start this session with the second half of the fourth unit, that is the section projection, development of surfaces. Right? Development of surfaces. You know what is development of surfaces? Suppose I have a solid surface. Okay, the solid will have surfaces. It will have base. It will have side faces. Right? So it will be a rectangular face for prism. It will be a triangular face for triangle, pyramid. Right? So if what is development is nothing but just opening out the surfaces of the solid and make it align on a planar sheet. Okay, that is nothing but a development. Suppose I have a cardboard box like this. What kind of prism it is? What is the base here? Rectangular. Okay, it is something like a rectangular prism. It is a rectangular prism. So the development of this prism, rectangular prism, just if I open these surfaces, if I cut this box and if I open it, okay, if I cut this box and if I open it, see here, if I cut this and open this, I will have my development to be like this. So what is the need of this? Anybody? Why we have to study this development of surface? Just the surfaces of a solid will be unfolded or rolled on a planar sheet, right? Then to that exact shape it will be cut and it can be folded back to form the solid shape, okay, whatever solid you want. Okay, that is nothing but development of surfaces. What is the need for studying this development of surfaces? Anybody? Why we have to study this development of surface? To form any shapes, okay, any solid surfaces, to form any component. Okay, if we know the development of that component, easily we can develop that and we can fold it to a required shape to get that component. Okay, so what is exactly what is the need if it is a sheet metal component? Right? If we exactly we can cut the shape. Suppose I have an automobile body, okay, the car structure body. So if I know the development exactly, that sheet alone I can draw it and I can use it for my product. Right? Otherwise, excess amount of material we will be using, that will be wasted. To avoid the wastage of material, okay, material usage, okay, for a component, if we know an exact development of that component, what you need, so that alone I can draw it and that alone I can cut it and I can use it for my, I can fold it and I can use it to form my, manufacture my required component. Okay, once I have folded it, the final thing I can either I can weld it or I can revert it to make that product. Right? So to avoid the wastage of material, we need to study the development of various solid. What is development? So development is development of surfaces. The solid surfaces, the surfaces of a solid, the surfaces of the solid, the surfaces of a solid unfolded or rolled on a or rolled. Why I am saying rolled or rolled means cylinder. If it is a cylinder, I have only rectangular sheet. I have to go for a process called rolling. Then if I roll that sheet, metal sheet of rectangular sheet, if I am able to roll it, then only I can form a cylinder. So either it is unfolded or rolling on a planar surface. Roll it on a planar surface. Is known as development of surfaces. Known as development of surfaces. Just look at this green. A cardboard box. It's just cut and it is opened out as they shown. Right. So this is nothing but the development, exact development of that cardboard box. Okay, it includes the base. Okay, 2 square bases. Okay, these are all 4 rectangular side faces, right? So then it is, if I fold it again and if I weld it, I will form the square prism. Okay, this is nothing but similarly you can have a hexagonal. So this is for prisms, I have to, prisms and pyramids, I have to unfold it, right? So if it is a cylinder, I have to go for a rolling. So if it is a cylinder or cone, I have to go for a rolling process to get the required shape, right? What is development? Just to see how we are going to draw the development. Okay, in your drawing sheet, just we will be drawing the projections of the given solid, and from that orthographic projection, right? So you will be going for developing the solid. Just look at a square prism, the same square prism, how it is developed. Just I have drawn the views, okay, orthogonal views, orthographic views. Then, depending upon this solid, we will be using the methods, okay. So here, it is something like it is open. Then, this is actually drawn from the views, okay, we will be getting from the views. You can see it. Just it will match with my front view, the third angle projection is drawn, okay, the 4 sides. So what will be the length of this square prism? 4 times the size, okay, and what will be the length of this rectangle? Tell me this length of this rectangle. Development, 4 times of its. So what is the length? I am asking you. 4 times of its base size, right? What will be the height of that one? Same height, right? So that is similar to that. The hexagonal prism will have 6 times of its base side and the height. Okay, that forms the rectangle. So just by folding, I can obtain the required solid. Go to next one. So where it is applied, application, to make a note, applications. So in an automobile industry, right, we need an exact sheet to be used, right? If we know the development of that portion of that component which we want, the sheet metal component on the surface of the car, so then that exact material alone will be used and it will be pressed depending upon what we need the shape. So to avoid material wastages in any automobile industry, this body will be constructed using it will be developed using development of surfaces. Then it will be formed with the required shape. Right. Similarly, you have shipping industries. Okay, shipping industry, shipbuilding, bodybuilding. We know the development exact sheets will be welded, riveted, and it will be formed to a shape of a ship. Right. Similarly, I have in any aircraft industries. Right. The aircraft structures, bodies. Okay, you know the development of the shape. Okay, you can see different shapes you have. It's a cylindrical portion. Here it's something like a conical and conoid, right? And we have different portions of sheet metal. What we have to do is to develop the structure of the aircraft, right? To form the structure of the aircraft, we have to develop first of all. Then we can go further. So, apart from that, any sheet metal application you can take the home appliance, any sheet metal application. The chimneys. So industrial chimneys, you can see it is a cylinder. On the roof you have the chimney. It is nothing but just a sheet. It is rolled to a shape of a cylinder. So chimneys, your home you have kitchen chimneys. So these are all prisms only. Okay, just sheets will be folded to form this. Similarly, cabinets. Okay, any cabinet. You can see your computer cabinet. It is of sheet metal. Okay, it is required amount of sheet will be cut and it is bent using sheet metal application. Then it is formed as a cabinet. So any cabinet in your machine tools, the machine tool cabinets. Okay, any sheet metal application if you see will be first of all the components will be developed. Okay, drawn using development. Then it is molded to form the prepared shape. Similarly, chimneys you can see ducts. Okay. Air conditioner ducts. Okay, these are all avoid material wastages. You can exact shapes you can develop it and you can form the components, right? So here This is about the application area of development of surface. Then what are the methods how to draw the development for various regular solids what we have been seeing. Right. So parallel line method, you have a method called parallel line method. So parallel line method, you see, it is generally used for prisms and cylinders and cube. Right. So if the solid is having regular side faces, right, then it is developed using parallel line method. So just drawing a parallel line from the two bases, and what is the base side you have, that one, what is the side you have, depending upon that you can get the development. Parallel line method, you can see this video. So this is the parallel line method, can be used for cylinders, prisms and cubes. Right. Then similarly you can see for cylinder, what will be the area of the lateral surface of the cylinder? No, the rectangular surface, the sheet of the, what will be the length of the rectangular sheet? If I have a if I want a cylindrical dia as D, circumference into its height, right? So the circumference of the diameter into height will give me, if I cut a rectangular sheet, and if I roll it, I will get the next method, radial line method. So it is generally used to develop a cones and pyramids. Right? You see this pyramids, tetrahedra, right? So any slant surfaces you have, okay, not and regular vertical surface, slant surfaces of solids, you can develop in radial line method. You can see it's a pyramid. So how I can develop this? Just I can fix my apex and I can open the pyramid. You can see here. Right. You can see this. So this is, if I have the base like this will be a pentagon. So the pentagonal one. So if I have a base like this, it will be an hexagonal pyramid. Just I can cut this one slanted location. Just I can unfold it so that I can get a pyramid. Okay. So what will be this length? It will be the base side. Okay. So how I can obtain this corners? I have to join it with a straight line. So how I will be developing this? Just what is this length? Slant edge length. Okay. Slant edge length. So that length, for that length, I can draw an arc. So fixing this apex, I can draw an arc for that length. Right. So along that arc, okay, the base is not an arc. If I am leaving it as an arc, if I roll that, what I will get? I will get a cone. Right. So on that arc, if I measure the base side and I cut it, and I will join like this, I will get a pyramid. If I fold it, I can get a pyramid. So this is the radial line method we will be using. Either we will be using the slant edge length for that radius to draw the, then otherwise we will be using a generator length as for cone. Okay. What is the true generator length? That we will be using it for cone. So apart from that, we have some more methods. You see here, triangulation method. So triangulation, one face is a square, another end face is a circle. So if it is transformed, the solid is transformed from a square to a circle. One, it will be something like this. It will be transformed in an irregular manner, right? It will be transformed. So this kind of solid, how I can develop it using triangulation method. What we will do is, just I will be forming, this is something like that. We will be forming triangles. Okay, I will be forming different triangles like this. Okay, I will be forming different triangles like this. Okay, that will be developed. Okay, and it will be rolled up, folded back to form this kind of transition solids. Okay, we will be using triangulation method. That we are not going to see. The one more method we have is approximation method. So approximation method, It's mainly used for sphere or spherical objects. Okay, spherical solids. Sphere you can see. The sphere is nothing but a ball. Okay, ball you can see the football. Football you have different pentagons, hexagons will be joined together. Okay, in an approximate manner I can form the sphere. Right. In an approximate manner I can form the sphere. Otherwise the same football rule it will be like this. Some ball will be like this. Right. So the rules will be formed. Okay. That will be developed and it will be stitched together to give me the shape of the sphere. Right. So that is called an approximation method. So any both way curved surface. Okay. Double curved surfaces. Okay. This is conoids. Okay. Double way curved surfaces in the sense, if I have an arc, if I revolve this, if an arc is revolved, I will get two-way curved surfaces. Right. Double way curved surfaces are available. So by revolving an arc, I will get a sphere. Okay. So this kind of solids will be developed using approximation method. Triangulation method is for transform solids. Right. This is about various methods. We will get into the problem straight away. Okay. Take the problem. The first problem. Draw the development. Lateral surface. Draw the lateral surface development of a hexagonal prism of base side. Hexagonal prism of base side 25 mm and height 60 mm. Height 60 mm is resting height 60 mm when it is kept vertically on the ground. When it is kept vertically on the ground with the base, with the face parallel to VP, with the face parallel to VP. So when it is kept on the ground, when it is kept vertically on the ground, with the face parallel to VP, with the face parallel to which is the face? Rectangular face. Okay, the face is nothing but a rectangular face as for prism. As for pyramid, it will be a triangular face. So you have face and you have faces and bases for prism. You have faces, triangular faces and base for pyramid. Right? Their face is parallel to VP. So it is kept like this. You draw the projection for this first of all quickly. Okay. Draw the projection into H pencil. Right. I ask you to draw the development of the prism. Okay, you need not draw the projection if it is a problem like that. So just, I know it is going to be a rectangle, 6 rectangles. Okay. So of side 6 into base, its base that is 25, 6 into, what is the length of the rectangle I will have in my development? 6 into 25, that is going to be the length. What will be the height of that rectangle of my developed surface? Same height 60, that is 6 into 125 is 150 by 60 rectangle will form, if I fold it, I will get a prism. Okay, that is the lateral surface alone I will get. That the other two bases, it's nothing but just a hexagon. Okay, two hexagon, if I fold it, I will get the prism. Right. So, as I told the method, it's a parallel line method I told. Just parallel line method is nothing but just from the two bases, I can draw a line parallel to my reference line. Okay, I can stretch out the by drawing a parallel line. That's why it is called parallel line method from two bases. So just I can draw parallel lines like this. Wait for parallel you draw it. Okay, just I can draw a parallel line. Then what I can do? So from where I am going to open, listen, from where I am going to open is, I am going to open this, the extreme edge. So I am going to cut the AP. So there I have stitched it or I have welded it. So AP I am going to to open it. That is the vertical edge I am going to open it. So just I am going to draw a vertical line somewhere in your convenient location. I can draw a vertical line. Right. So vertical line. So this is nothing but my A and P. That is the location I am going to open the solid. So that is the location I am going to hold it and form the prism. So I can have a notation A and this is my P. So in your development, the notations you will be giving in capital letters, right? So all the notations you will be giving in capital letters. So this is my first vertical edge, that is A and P. So from there I am opening, from there I am going to close that solid, form that solid. So then what is the length I have to draw vertical line? It is 25. So this 25, you can measure it in your compass. So 25 for each 25 length, I can have 6 faces. And have 6 faces. Right. So on the stretched out line, I mark 6 locations. So this is going to be my location of B. Next one, this is C, D, and E, F. What will be my final one? So already 6 notations I have got. What will be my final one? Again A would have. The A and A, the same location I have trimmed it and I have forming on the same edge itself. So again I will get the same notation A. So that is the same corner, so same vertical edge where I am opening this solid, right? So where I am going to stitch this solid. Okay, that is the location. So in your development, the starting notation and the final notation will be same. Right. So this is how I can end it up. So what will be the length? So the length will be definitely the length of this development will be definitely 6 into 25. 6 into 25. It is my 150 mm. Right. So then I have to show the vertical edges where I am going to fold it. So this is a prism where I am going to fold it. So these locations are B, from B, C, D. So that is the location I am going to have my folding. So that location also you have to show it as edge. So if I fold this edges at this appropriate location, I will have a hexagon. So similarly, you can give the notations for the top base also. B, Q, again P. Right. So this is nothing but the development of a prism using parallel line method. So line drawn from 2 bases. Right. You have any clarification in this? Very simple, right? So we'll have, if it is a square prism, I will have only 4. If it is a pentagonal prism, I will have only 5. Right? For this size, I will have only 5 size. Right? So take the problem, continue the problem. So this is the problem, continue the problem. It is cut by a plane. Prism, it is cut by a plane, cutting plane. It is cut by a plane. It is cut by a cutting plane which is perpendicular to VP. So what is this one? How it is cutting? I have kept the solid here, prism. How it is cutting? The cutting plane is cutting. So a plane I am going to introduce to cut this solid perpendicular to VP, right? A plane I am going to introduce that is going to be perpendicular to VP, cutting plane perpendicular to VP and inclined to HP, right? Inclined to HP. How much degree? Inclined to HP it is not, so I am going to give that is 65 degree. 65 degree inclined to HP, right? and 65-degree inclined to HP. 65-degree inclined to HP and bisecting the axis. Bisecting the axis. Now can you show the cutting plane, mark the cutting points, rotate the cutting, you need not draw the sectional top view, right? Rotate the cutting points and the fixed plane to 65-degree to HP by bisecting the axis, right? Draw the lateral surface development. Draw the lateral surface development of the retained portion of the hexagon. Retained portion of the hexagon. Okay, that is the problem. So quickly you represent the cutting plane. You represent it on BP, right? So it cuts at a 60-degree inclination to HP. So if you represent the cutting plane, it cuts both the base, right? So on base I will get 2 cutting points, right? So and it cuts 4 vertical edges, right? So starting from here, bottom, I can give the cutting points for a visible cutting points. I can mark it 1, 2, 3 and 4 on the base. Again I have to come back on the same manner along the cutting plane, looking for hidden cutting point. So there I will have hidden base cutting point, then top base cutting point, then hidden vertical edge point, then hidden vertical edge point, again hidden bottom base point. So totally I will have 8 cutting points. Listen here, how I have to transfer these cutting points to my development. How I have to mark these cutting points to my development. Once I have able to mark that in my development, the retained portion alone I can darken it. Okay, if I fold that, I will get the final part. That is the retained part development. So how I can able to mark these cutting points to my development? You see, carefully look at the notation where the cutting points fall exactly on which vertical edge or on which base edge. Right? That is very much essential here. So you see here, first of all, I will come back to this base cutting point. Listen. So you look at this vertical edge cutting point. Right? That is cutting point 2. Cutting point 2 is on which visible edge? Visible BQ. Right? It is at BQ. Cutting point 2 is at BQ. Similarly, 7 is at FU. So you see here, BQ I have in my development here. FU I have here. Okay, on that somewhere I have to mark exactly cutting point 2 and 7. So how I can mark it? Anybody? Just I can extend a horizontal parallel line from there. So just I can. So otherwise what you can do is you can measure this height. Okay, from the base what is this height? You can measure it. Cutting point height on appropriate vertical edge you can mark it. Right? Otherwise you draw a parallel. Cutting point 2 is on edge, vertical edge BQ. So cutting point 2 is on vertical edge BQ. So you just mark that on vertical edge BQ. So that is my cutting point 2. Similarly, cutting point 7 is my vertical edge FU. So FU I have here. So that is my cutting point 7. Right. So this way I can mark other 2 vertical edge cutting points, that is 3 and 6. So 3 and 6, it falls on CR and it falls on ET. Right? CR. Similarly, so CR is this one. This is going to be my cutting point 3. This is then ET. ET is there. Here I will have my cutting point 5. So this is about vertical cutting point. So cutting points on the vertical edges. Right. Parallelly I can draw it, extend it. So what about this base cutting point? Anybody? How I can transfer this base cutting? What is the base? How this base is developed? It is seen as a line in my development. Similarly, top base is seen as a line in my development. Right. So you see these cutting points 1 and 8. One is cutting point 1 is on which base edge? A, B. A to B. So you see in my development AB is there. Somewhere in between this AB I have to mark my cutting point 1. Similarly 8 is on FA. It is behind FA. So that is nothing but F2A. Somewhere here in between I have to mark my final cutting point 8. Right? So how exactly I can transfer that location? How I can transfer? This is a front view projection. So you don't know the exact location in the front view. What I can do is, I can extend these cutting points to the top view. Here I have exact length of the base sides. Right? Here I don't have the exact length of the base side in my front view. So this cutting point on the base, which falls on the base, okay, that should be projected to the top view to get the exact location of the cutting points on the base. Right? So just I can project these base cutting points to the top view. Okay, to the top view. So wherever it cuts, that is along A and B, that is my cutting point 1. Along F and A, that is my cutting point 8. Right? Similarly, this top base cutting point, I can project it on the top view since it falls on the base. So on RS, I will have my cutting point 4. On ST, that is my cutting point 5. So now you tell me how I can transfer these distances on an appropriate location. 1 and 8. 1 and 8 is on the bottom base. So my 1 and 8 on the bottom stretch out line. That is stretch out line for the bottom base. So I have to measure distance of 1 from A in my top view. What is the distance from A to 1? You measure it in your compass in your top view. Is it clear? So the base I have A to B length is 25. That is in between A to B. I have to mark A to 1 distance. Okay, in your compass you measure it. That you transfer it on the bottom base stretch out line. This is going to be my cutting point 1 on the bottom base stretch out line. Similarly, what is the distance for A? Either from F or either from A in the end. Right? So from F, what is the distance? You measure it. So from F, I can transfer it from F. So again, 8 is falls on the bottom base. So bottom stretch out line, I can mark this cutting point 8. Right. So similarly, I can mark the top base cutting points 4 and 5, which is projected in the top view. From the top view, measure that location exactly on the corresponding place. Okay, so where it is exactly R to S. So R to S, R and S. In between R and S, I should have my cutting point 4. Then 5 will be in between S and T. In between S and T, I should have my cutting point 5. You can see here, 1, 2, in a sequence it will go. Right? 1, 2, 3, then 4th cutting point in between RS on the top base I should mark. 5th cutting point in between ST on the top base I have to mark it. So how I can measure that? So from R to 4, what is the distance in your top view? That is measured it from R to 4, R to S. That is going to be my cutting point 4. Similarly, from S to 5, what is the distance you can measure it? S to 5. So that S to 5, I can measure it here. That is my 5 cutting point. This is wrongly written as 6. Right. This is 1, 2, 3, 4, 5 and 6. Right. So I have totally 6 cutting points are neatly marked. Now what I have to do is it clear? So if a cutting point falls on a vertical edge, directly it can be projected. Right. If it falls on the base, that should be projected to the top view. In the top view only I will know the exact location on the base side. So that location has been transferred properly on the exact base sides. Right? Either this bottom base or top base sides, exactly you have to mark it. Is it clear? You have any clarification? Right. Then, which is my retained portion here? The bottom portion what you have drawn in your thing. So just you connect these cutting points in a sequence with a straight line or curve. With a straight line, I have to join these cutting points. Okay, to show the cutting location 1 to 2. You can connect it with a straight line. 2 to 3. You can connect it with a straight line. 3 to 4. Then 4 to 5 with a straight line. Then 5 to 6 the straight line. Then 6 to 7, the straight line. Then 7 to 8, the straight line. Okay, so this is the portion, is my retained portions development, right? So this is the bottom portion, okay, bottom portion. So the top portion is removed off. So the bottom portion alone, I can darken it and I can show it in my development. So this is not the development. I have to show I have to darken the vertical edges also from Q to B. So now this is my retained portion of the solid, how it is developed, right? Retained portion I had, right? After sectioning, this was the retained portion I had. If I open this, okay, if I open this surface like this, okay, I will get the retained solid. It will be similar to this. Is it matches? Okay, suppose similar to this. Okay, the retained portion I will have. Right. If I fold this, the retained solid, I will get it. Okay, the size differs. Okay, the same way it should be folded, I will get the retained portion of the solid. Right. Again, a hexagonal prism of base side 25 mm and height 60 mm is kept vertically on the ground with its base such that a face parallel to VP. Right, full stop. It is, the next one, it is cut by a, it is cut centrally drilled with a circular hole, centrally drilled with a through hole of dia 34 mm. Of dia 34 mm. Listen, the cutting plane, instead of a cutting plane, it is a circular cutting plane. Listen, it is a circular cutting plane going to drill it. Okay, centrally in the sense what? Exactly in the middle. Okay, exactly in the middle. It is centrally drilled. Through hole means what? Through. From front surface to the rear surface is going to be cut. Okay, it is all the way through. It cuts the solid with a circular hole of diameter 34 mm. Right. You just draw the prism, the projection of the prism, draw the lateral surface development of the hexagonal prism alone. Make it fast. So here, this end is over. The development is over. Right. So the cutting plane, it is a hole. Okay. Centrally drilled hole. So centrally in the middle of the axis, that is 30 mm. So centrally a circle of diameter 34 mm. I have to draw it. That is nothing but my cutting plane. So it cuts through all. Right. It cuts through all. Now the cutting points, I am going to mark it for my convenience. Listen all of you. So either you can divide it. So the cutting points I am going to mark for my convenience. You see here, this is the cutting point I am going to have where it intersects the vertical edge. That is B and vertical edge B. That is a visible edge B. So B it intersects. So there I am marking the cutting point as 1. Right. The next vertical edge, visible vertical edge it cuts is C. Right. The circle cuts is C. That is my cutting point 2. So where it cuts, that is the location 2 I am marking. Then it cuts So it goes to a surface, slant surface. This is the portion in the front view is nothing but my slant surface of the, in a front view it is a slant surface, it is not showing the true length of that base. So here tangent location, at the tangent location I am marking the cutting point as, that is the extreme tangent location as 3. Then it cuts the vertical edge, front vertical edge, that is my cutting point 4. I am marking it, that is again C. Similarly again B, it cuts the vertical edge B here, that is my cutting point 5. Then I have extreme in this slant face of the front view, right, that is a slant surface in the front view, that is my cutting point 6. Right. So totally I have marked 6 cutting points in my front view. So these 6 cutting points has to be marked in my development. Right. So these 6 cutting points has to be marked. You see here, this circle 6 points will be available in my front face, front side, and the same circular cutting points will be available in my rear side of the hexagon. So front side in the sense what? The face AB, visible face AB, visible face BC, visible face CD. Right. So on that I will have a circular cutting point, I have to mark it. Similarly hidden faces, that is DE and EF and FA. On that face also I will have a circular hole. So if I open it I can see 2 holes in my development. Is it clear? If I open it I can see 2 holes in my development. Since the hole is drilled all the way through, okay, it comes through behind the face. Right. So on a visible faces I will have a circle. On a hidden faces I will have a circle. I have to mark the cutting point. Totally 10 locations I have to mark the cutting point. You see, look at AB. So first of all you mark this 1, 2, 4, 5. It is clearly I can mark it by drawing a horizontal line, extending horizontal line and marking it on a corresponding vertical edges. So 1, 2, 4 and 5. You mark it on a corresponding vertical edges directly by extending projector. So 1 and 2. By drawing a projector from 1 and 2, I can draw. Listen all of you. How I can, where I have cutting point 1 in the visible face, exactly B and exactly on B vertical edge. So from B, on B I have to mark my cutting point 1. Cutting point 1. Similarly, the same cutting point 1 is available at the behind hidden vertical edge also. That is what? F. So F here. Okay. I have to mark cutting point 1 again. Right. Similarly, cutting point 2 is available at 2 locations. Visible edge C and hidden edge E. So cutting point 2 on the same thing, visible edge C. I have cutting point 2. Then E here, cutting point 2. Right. Then this 4 is available at C and E again. C I have here 4. Then similarly the same 4 is available here also, that is negative point 4. Right. Then cutting point 5 is on vertical edge B and F. So B is here, I can mark my cutting point 5. Similarly F, I can mark my cutting point 5. Right. So up to this 1 and 2, 2 to 1, 4 to 5 and 5 to 4. So that portion you can see, look at this portion. It is on a flat face, okay. It is a parallel face, okay. This portion, how I can draw that on my development? Just this arc, okay. Just this arc I can draw it in compass, okay. In between is 5 and 4 and 4 and 5. This location, I can draw an arc of radius 17. So for that I have to mark the center for that. First of all, you can draw a projector from the center of the hole. So center of the hole. So here exactly in the middle, I have my circle center. 1 is the behind center. In the middle, I have center. 1 circle center. Okay, 2 locations I have center, circle center. So using that location, you see here, this circle, it cuts the flat surface of BC. So in between BC I will have the circle center. Similarly, the circle center again in the behind surface, flat surface is EF. So in between EF I will have my center. So I can mark the central location here, BC. From there I can mark the center. Or exactly mark the center there. On face BC as well as face, behind face, parallel face, EF. Right, I can mark the center. Now what I can do to finish, to show this arc alone. Okay, it is a constant arc. Since it falls on a parallel surface, so using a radius of 17, using this as center, from 5 to 4 I can draw that arc. From 5 to 4, a circle I can draw it. 5 to 4. So what should be this radius of this arc? 17. Exactly 17. Since it falls on a flat face, the circular portion falls on a flat face, that will be exactly 17 radius. Right. Is it clear? So this portion you have to finish it first of all by marking the center and the cutting points which falls on the vertical edges. So what about this cutting point 6 and 3? Again 6 I have somewhere here I have to get 6. Somewhere here I have to get my 3. Similarly here somewhere here I have to get my 3. Somewhere here I have to get my 6. So here I have to get my 6. Somewhere here I have to get my 3. This is 3. Again it will be 6. So it is on a slant face, okay, in my front view. It is not a parallel face, right? Inclined face in my front view, right? So how I can mark that? What I can do that? So it is exactly on the central line, that I know. 6 and 3 is on the central projector. So exactly on the central projector what you have drawn. But what is the exact location? I have to mark it on this face AB. So 6 is falls on AB as well as FA. AB and FA. 6 I will have. Similarly, 3 is falls on CD and DE. So CD 3 and DE I will have another 3. That is a hidden face. So how I have to mark that exact location? Anybody? What I can do it? I can project it to the top view. I can mark that base location here. From there I can mark the 6 and 3. So what I can do? I can project this 6. The top view, similarly 3 to the top view. So the base location, that is, this is my 6, this is 3, 3. So from A to 6, what is the distance? To measure it, where I have to mark this 6. From A to 6, what is this? This is nothing but my base. So A to 6, I have to mark it in between base AB. So in between base AB. So A to 6, in between base AB, I can mark the 6 at AB. Right. 3 is on CD. So in between CD, I can mark this 3. 3 distance, I can mark 3. So this is my 3. Similarly, D to E. D to E I have to mark 3, D to E, D to 3. I can mark it. This is again 3. What I can do it now? To mark the location. Just I can project this, the central line. Mark 3 again. This is my location of 6. Right. This will give me my 6 location 6. Cutting point 6. This is 3. And this is a point 6. So is it clear? Listen, is it clear? Do you have any clarification in this? So either you can transfer these distances, A to 6 distances, to the base or directly to the central projector what you have drawn. Right? From A to 6 directly you can mark it. Central line, the 6 and 3 it falls on the central line. Okay, central projector line. From A to 6 you can directly mark it. From similarly F to 6, from F to 6 I can directly mark it. Otherwise it falls, as a procedure it falls on the base. So you mark it on the base, then you project it to the central location. that is going to be the exact location of the cutting point 6 and 3. Right. Now you see, I have to connect 1, 6, 3 as an arc. Right. So this arc will not have a radius of 17. Isn't it? It won't have a radius of 17. It will be a different arc. So you have to draw it as a 3-point arc. Okay, I have 3 locations. I have to connect it with a 3-point arc. Right, 3-point arc means it will have a different radius. Smoothly, the circle you have to draw it, tangentially it has to connect. Tangentially it has to connect. It won't have a radius of 17. If it falls on the flat face, it will have a 17 mm radius. Since this portion 342, that is 561, it falls on a slant face in my front view. Right. So it will have a different radius. Just smoothly you connect with a 3-point arc. Smoothly connect with a 3-point arc like this. This development, if I fold it, I will have a hole, exactly a circular hole seam in my front view. I will keep this solid. Okay. So this is the way you have to draw a 3-point arc. So the retained portion, vertical edges, you have to show it. So this is one of the vertical edge I have here. Here. Then the base. See here, carefully you draw the 3-point arc. One more thing you know, this is the radius, a constant radius. Directly you can use a compass for this. Right, this portion. I can use a compass, that is radius 17. Right, that's 5 to 4 and 1 to 2 region, I can use radius 17. But this portion 165. It won't be a 17 mm radius, it's a different one. Using 3 points, you connect it with a free hand, a smooth curve. It should be a circle. You see here, connecting these 3, it should be a circle. Circle-like thing. Exactly connecting this diameter. It should be something like a circle connected. Okay. Then if I fold this development, I will have a prism like this, drilled with a centrally drilled with a hole. If it is kept parallel to BP, one of its face parallel to BP like this, I will get. You can see it. Right? Do you have any clarification in this? Take the problem. A vertical chimney of circular cross section, diameter 400 millimeter, is on an industrial slope of 30 degree to the horizontal. Full stop. The shortest distance of the chimney from the roof, 350 mm. Draw the lateral surface development of the sheet metal required to form the chimney. So you see this chimney, see the diagram you take. So this is a problem, just a chimney of circular cross section in the sense what? It is something like a cylinder. It is on the industrial slope. Okay, over the industrial slope, that slope is 30 degree to the horizontal. Right. So some other data is given. The shortest distance from the roof to the chimney, it is 350. So you can see this diagram. So I have an industrial slope. I have an industrial slope like this. So this slope is what angle it is? The slope is 30 degree. Right. The slope is 30 degree. So over this slope I have a chimney. So that chimney having a circular cross section. Right. It is a cylinder-like thing. It is a circular cross section. It has, right, this is a circular cross section. This has a diameter of what? 400. This has a diameter of 400. So one more data is given. What is this 350? You tell me. Which is shortest distance of the chimney, right? From the roof. So this is 350. So in the problem was given this length. It is 350. You see, these are all in 400, 350 mm. Can you draw it in your drawing sheet? No. So what you have to do? You have to adopt a scale. So scale, what scale I can go for? I can reduce the size. So reduction scale I can adopt. So what is the reduction? 1:10. So what you are going to draw it as 40. So actual is 400. So what is the scale? Scale, how you will write? Carefully you adopt a scale. So use appropriate scale. In the problem it will be given use appropriate scale. So scale you are going to adopt is this. Scale is, we are going to draw it as 40. So drawn size by actual size. Drawn size is 40. So actual size is 400. So it will be 1/10. So it will be 1:10. So your scale you are going to adopt is 1:10. So in your drawing, once you have drawn the development, so below that you have to write the scale is 1:10 you have used. Okay, but during the dimensioning of your development, you have to use the actual value 400. You have to write it, right? So, but you will be drawn to 1:10 scale. Is it clear? Now, so this is a cylinder. Cylinder, you see, cylinder with a cutting plane. Okay, it is something like this. Whole thing, it is something like a cylinder. Cylinder, it's cut by a cutting plane that is perpendicular to VP cutting plane, which is 30 degree inclined to the horizontal. So you are going to draw a cylinder, 30 degree horizontal line. You can draw a 30 degree line, something like a slope. It's 30 degree, right? Then somewhere here, somewhere at this location, or you can measure from that. I can measure 350, right? 350 you can measure. You can draw a vertical line for 350. Then horizontally what length I have to draw for this chimney? 40. So 25 and 40. So then I can close this to this slope. Right. If you have to divide it into 12 segments. Right. You can notate it. Then you can project these points to your front view. Right. So you will have a base here, you will have a base here. Then what you have to represent? This will be something like a cutting plane. The 30 degree, it will be something like a cutting plane, cuts the cylinder fully. Okay, it cuts all the 12 generators. You have to mark 12 cutting points. Okay, so first of all you finish the projection quickly. Draw the front view. Then this cross section is a circle, you know, it's a cylinder. So the top view I have drawn. The top view is divided into 12 segments. Okay, to mark the generator locations. So these 12 segments will be projected to the front view as usual, like your solid problem. So these 12 segments, generator location, the front view also marked. So you try to show the generators, all the 12 generators in your front view in 2H pencil. Right? It should not be a dark one. Listen, it should not be a dark one. Then the cutting plane here, it's something like a cylinder. So the cylinder you can develop, cylinder, the development, lateral surface development of the cylinder is nothing but a rectangular sheet of length equal to the circumference of the cylinder. Right? Circumference of this circle. What is the circumference of this circle? Pi d. Okay, the diameter is 40, so it will be pi d. And the height of the rectangular sheet will be the height of the cylinder. So here the height of the cylinder is not given. So whatever location you have marked, so that is going to be the height. Okay, this is going to be my height. So including this 350, so whatever portion you have represented in your front view, depends upon this you will have the height. So the development of a cylinder, it's very simple. As usual, using parallel line method, I can develop the top base my development first generator somewhere here. Okay, suppose this is where I am opening here at A, generator A. So this is suppose my generator A, right? Then, so what length the cylinder, development of the cylinder will be? It will be pi d length. Pi d length is nothing but my 3.14 into this 40, right? 40, it will be 125.6. So this length is going to be my 125.6. So this is, so that is nothing but my this circumference length of the cylinder, right? So then this height is nothing but depends upon the height. Okay, this is my h, height of the cylinder, right? So this is the lateral surface development of a cylinder alone. Now it is something like a cut cylinder. This chimney is something like a cut cylinder in your problem. So it is cut by a plane. The cutting plane here is nothing but my industrial slope. The slope is 30-degree incline. So you have represented in your front view a 30-degree line, that is something like a cutting plane line. That is actually, it is nothing but a slope, right? Industrial slope, that is 30-degree incline. So once I have shown that cutting plane as well, it will give me 12 cutting points such that it cuts all the 12 generators. It cuts all the 12 generator sinks. So I am getting 12 cutting points. Okay, in a sequence you mark the cutting points, okay, visible cutting points for the visible generators and hidden cutting points for the hidden generator. As usual, something in you, like your section of solids, you can represent 12 cutting points. Now, this development is, it's a rectangular sheet for a cylinder. So I have generators here, 12 generators. These 12 generators has to be shown in your development first of all. How I can do that? So this 125.6, either using construction procedure, you can divide it into 12 segments, or 125.6 you divide it by 12. So what is the value you are getting? That divisions 10.4 I can cut it. So 10.4 you can measure it and you can get 12 divisions. So and neatly you mark the 12 generators and try to show the generators, 12 generators in your development in 2H pencil. It should not be a dark one. In 2H pencil you try to show the generators also. Then as usual you know how to mark this cutting point. Okay, straight away I can project it. Okay, cutting point 1 is on generator A. Okay, I can straight away I can project it, I can mark the cutting points on the corresponding generator. Then you join the cutting points in a sequence with a curve or straight line. Curve. So that will be a, then you can try to show the retained portion. Try to represent the generators and cutting points in your development. You have 12 generator locations. You try to mark that 12 generator location and try to show that 12 generators in your development also, right? So generators will be from A to B, it will be 125.6 divided by 10.4. 10.4 you mark it and try to show all the generators in your development in 2H pencil. Something like this, right? Is it clear? Listen. So actually it is a sheet. Development of a cylinder, it's nothing but a rectangular sheet. I can form a cylinder, right? So these generators will not appear in your sheet, right? Just it should be in 2H pencil to mark the locations of that points of the circumference, right? So what then I have the cutting points, 12 cutting points. It cuts 12 generators. So you see the cutting point in a sequence you have marked. So cutting point 1 is on which generator? A. Cutting point 1 is on A. So directly I can project this cutting point as usual, something like prism, how you have shown in the last problem. Just you project the cutting point 1 to projector, generator A. So similarly the same location is there in your development at the end, other end. So that same A will be projected. So same cutting point 1 will be projected to the generator, which will be at the end also. So same A is available at the end also. So this is my cutting point 1. This is again my cutting point 1 in my development. So similarly cutting point 2 and 12. So similarly 1 and 2 and 12. 2 is on cutting point B, 12 is on cutting generator L. So cutting point 2 is on generator B, 12 is on L. Similarly 3 is on C, generator C, 11 is on K. So 4 is on D. So correspondingly you can project it similar to this on the corresponding generators in your development. You can mark that points. Okay. Now this is my cutting point 2. 3 is here, 12 is on L. Right, then this 12 is on L, then I have cutting point 1 is on again on A. So in a sequence I can mark these cutting points. Then these cutting points should be joined as a curve. Right, it should be, since it is the cutting points of a cylinder, so for cutting points of a cylinder and cone, it should be joined in your development as a curve. Right, apart from cylinder and cone, if it is a prism or pyramid, it should be joined as a straight line. Right, so here using your 2H pencils, try to get a smooth curve first of all. I will get a curve like this. Right, see here, I can join the curve like this, okay. Then, which is the portion of your chimney? In your front view, which is the portion of your chimney? This is the portion of your chimney. Just darken the chimney portion. Right, similarly here, the top portion of your development, okay. That is going to be my chimney portion. Just that alone you darken it. So this portion is my chimney portion. Right. So this is the chimney. So you should not darken the generator. Okay, it's a sheet. Right. Rectangular sheet. Something like this shape. If I roll it, I can form a chimney like this. Right. I can fix it on my roof, which is 30-degree inclined. So this is the development of the chimney. Draw the sheet metal development of a, what pipe this is in your workshop here? L pipe. Shown in the diagram. L pipe shown in the diagram. Okay, this is the diagram. Right. So what is this L-shaped pipe? It is both diameter is 40 mm and the height is given, length is 20. So from this portion is 20, this is 40. Okay. You see here, it's something like your previous problem. So up to this, it's something like a chimney, previous problem. So this is again something like a chimney. Okay, I'm not going to do it. You do this as a homework. Right, you do this as a homework. You see here, similarly it is an L pipe. So to development you have to draw this. So this is a portion A of a cylinder. This is another cut cylinder of B. This is cut cylinder of A, this is cut cylinder of B. Right. So the diameter is same, everything is similar to that. So you can represent the cutting points. One thing you have to careful here, so the circle I should have represented it here. It will be still better. So this view, side view, right, or top view I would have drawn here, this circle. Both are same. So even though you represent carefully here, see here, this 12 division, whatever you have divided, listen all of you. So this is my division. Okay, it's okay. So whatever the intersection of this pipe, okay, both portions of pipe A and B, so it is something like a cutting plane. It's something like a cutting plane cuts the cylinder. So it's something like a cutting plane cuts this length of a cylinder. Okay, this length is totally 60. The 60 mm length of a cylinder is cut by a cutting plane, something like this. Similarly, this 60 mm portion of a cylinder cut by a cutting plane like this. So you have to draw the development of this portion of cylinder, separately. So you have to draw the development of this portion of cylinder separately. Right. So this intersection, it acts something like a cutting plane. So I can mark the cutting points carefully. So cutting point 1, I'm going. So I have my this generator notation. Here I have A, B, C, D, E, F, G, H, I, J, K, L. So what are hidden here? I, J, K, A, B, C are hidden. right? So my cutting point, I'm going to give the cutting points from here. 1, 2, 3 in a sequence like this. I'm going to give. This is my cutting point 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. Right. So these cutting points you can mark it. Is it clear? You have any clarification? Now you see your cutting point 1 is where I have in which generator? Carefully you see. In cutting point 1 I have it cuts the generator D, extreme generator D. I have generator D here. So cutting point 1 is on D. Listen all of you. Now I am going to open. Similarly this D I will have here. This A is here. Similarly, you have to mark your generator location. Then cutting points, 12 cutting points you mark it. So the cutting point 1 falls on generator D. Cutting point 1 falls on generator D. So 2 and 12 is on C and E. Right. So which one, from where I have to open my development? Carefully you watch, from where I have to open my development. So previous problem you had your generator, extreme generator as A. So you have opened you have started your development from generator A. Here I am going to open from here. So I have to start my generator from D. Right, I can start it from D. So my starting generator is D. So end generator location again it is D. Here. So you have to open this development from D, exactly from D. So since you from the extreme generator you try to open your development. So previously we had the extreme generator as A. Here the extreme generator D I have. The A generator I have in the middle. So what? Either I can give my extreme generator A. I can start my notation A from here. I can give my notation. That is one thing. If you have given the notation here, started from here A. So your extreme generator for this component will be D. So either you have to started your development notation from here A, B, C, D. You have in an order you should given. So then your generator will be extreme generator will be A. So I have something like your previous problem. Now my extreme generator is D. So I have started from D. So from D, what is the next generator? D, E, F, this is G, H, I, J, K, L. L, after L what I have? A. Then I have to start A, B, C and D. So with this it will end. Right. And similarly the notations here. So I can start again. Here also I'm going to open from D. So I can start it from D. So this is my D. E. So this is also D. E. Be careful in notating this. Otherwise you can notate it as it is from A, B, C, D. Right. The cutting points carefully you have to mark it. The shape will be in a different thing. Okay. Now you won't get the shape similar to your previous chimney problem. Right. So chimney problem, if you want to get something like your chimney previous problem, you have to notate it. And carefully you have to notate it. So whatever extreme generator you are getting, you open from that extreme generator notation. So starting from D and D. Right. So otherwise you have to notate it properly in your circle, not like as usual. So you can notate it from here. You can keep A as an extreme generator. Okay. Is it clear? So once you have notated that, then it is something like cutting points, as usual you can represent it. The intersection line is nothing but my cutting point. Intersection of these two points, that line represents my cutting point. I can mark 12 cutting points since it pass through 12 generators, all 12 generators. I will have 12 cutting points. These cutting points has to be marked by parallelly projecting that, similar to your previous problem, just I can parallelly project it. So this is my cutting point 1, right. So this where I have 1, this is my cutting point 1. In a sequence you will get something like, if you have properly rotated your your development at an appropriate location, whatever you have in the extreme generator. From the extreme generator, if you have opened your development, okay, if you have started your development, you will get a cutting points in a sequence, something like this, right? So by joining this with a smooth curve, I will have the development portion. So this is a portion for B. This is a development portion for B. Similarly, I will have a development portion for A also. Similar to that, I can project these cutting points. This is the development portion of A. Right, is it clear? So if the height is differed, so the height will differ. Right. So it's similar to your previous chimney problem. So carefully mark the generator locations. Right. See, radial line method, you take a lampshade is formed, a lampshade is formed by cutting a cone of diameter, a diameter 400 mm and height, diameter 400 mm and height 600 mm. Height 600 mm. Full stop. Okay, it is a cone. Right, it is a cone. How I can develop? First of all, you will see that you draw the development of a cone first of all. Right. Then we will proceed the problem how it is cut with a cutting plate to form a shape of a lampshade. Right. So we finish the problem. So it is first cutting plate. So cone diameter 400 mm. Height 600 mm. First cutting plate cuts the cone parallel to its base and perpendicular to its axis. Perpendicular to its axis 10 mm from the apex and 10 mm from the apex. So first cutting plate cuts the cone so parallel to its base. So parallel to base, perpendicular to axis. So perpendicular axis in the sense perpendicular to, if I have a cone vertically like this, it's perpendicularly it cuts. That is perpendicular to vertical plane, it cuts the cone. And parallel to the axis means parallel to horizontal plane. So a parallel cutting plane, parallel vertical plane cuts the cone at a location of 10 mm from apex. So from the apex, 10 mm below that, you have to represent a parallel cutting plane, parallel to the reference line, you have to represent the cutting plane that cuts the cone. That is the first cutting plane, full stop. The second cutting plane passes through extremities of base and 25 degree inclined to and 25 degree inclined to the base. 25 degree inclined to the base. So 25 degree inclined to base. So is it clear this problem? Right. Full stop. Draw the lateral development of the sheet metal required. Draw the lateral development of the sheet metal required to form the lampshade. Which falls in between the cutting plane, two cutting planes. You see, I have a cone like this. So I have a cone, vertical cone like this. So diameter is given, height is given, right? So it is cut by two cutting planes, not right. So one first cutting plane is cutting parallel to its base. So axis I have first cutting plane cuts parallel to its base and perpendicular to the axis 10 mm away from the apex. This is my apex. From here 10 mm away from the apex, the first cutting plane cuts something like this. So this distance is 10 mm. So this is my first cutting plane. Right. The second cutting plane cuts the cone. Second cutting plane cuts the cone. Right. Passes. It is a vertical plane. It is a vertical plane. Passes through the one of the base extremities of the base. Extremities of the base in the sense extreme points of the base. Which is the extreme point here? This is an extreme point. This is another extreme point. So another cutting plane is passed through this extreme. So and it is 25 degree inclined to the base. So from the base it is 25 degree inclined and it is passed through the one of the extremities. So the second cutting plane is like this. It cuts the cone. So this is my second cutting plane. So the first cutting plane parallel it cuts, second cutting plane it cuts like this. So this angle is 25. So this angle is 25. Right. So which is the portion of my lampshade here? So the in-between portion, this portion is my lampshade. So the in-between portion, so if I try to show in my development, so that if I roll it, it will form the development of the lampshade. So this is my lampshade portion. So what we can do it, so first of all you have to try to draw the development of a cone. First of all, what is the development of a cone? It will be a segment of a circle, right? It will be a segment of a circle, right? So it depends upon the base and its generator length. Okay, so the generator length is going to be the my circle radius, right? The generator length. So what is the actual generator length from where I can get it? The extreme. Okay, the extreme generator in the front view will give me the generator length. So for this generator length, I can draw a circle, segment of circle, depends upon my base diameter. So that will give me the development of the cone. So what is the generator length? First of all, you have to find out. Only you have to draw the projection. First of all, so what is the projection for this cone? It is diameter 400 and height is 600. So you have to use a scale. What is the scale you have to use? 1:10 again. So the scale I can use it. The scale is 1:10. 1:10 scale you have to use it. Then you draw the development. You draw the projections of the cone. Make it fast. You draw the projection of the cone. See here. So the development of a cone alone, as far as the development of a cone alone, you know, it's a segment of a circle of radius equal to the generator length. Right. So the radius equal to the generator length. Which is the generator length? From which view I can measure the generator length? The original generator length. So original generator length in the sense which generator is parallel to the vertical plane. If a cone is kept, which generator will give me the true length in my front view? Which generator will give me the true length in my front view? OG and OA. So only the extreme generator will give me the true length in my front view. So the extreme generator is OG and OA. So I can measure this OG or OA. It's nothing but my generator length. OG or OA is my generator length. Alright. To this generator length, you measure this. Okay, extreme generator. This generator OF and OG, whatever generator falls in between that won't give my actual true length of my generator. Right. So the extreme generator alone will give me the generator length. So by measuring OG, right. So you can mark the center of the your development, say O, right. Then you can draw a generator length for any inclination, right. So what is the generator length you measure? This is my generator length, right. Say this is OA. So for this generator length, so OA, so I can draw an arc. So I can draw an arc. So using this, I can draw an arc for this. So whatever distance you are getting in your front view, OA and OG, that is your generator length. So this is my generator length in your front view. So OA and OG, whatever you are measuring in your front view, that is my generator length. For that, this is my generator length. Right. For this, I can draw an arc. Right. So along this arc, what distance I have to mark it, measure it, to develop this cone. Anybody? To develop this cone, what is this arc? What is this arc? This arc is nothing but the circumference of this circle. Okay. So I have to open this arc up to the circumference of this cone base diameter. So what is the cone base diameter is 40. So 40 into pi, that is pi d. So what is that length? It will be 125.6. So 125.6, along this arc I have to measure it and I have to end it up. So I have to close it. That is going to be my cone, development of the cone. Can you measure 125.6 along this arc? It is not possible. Right. It's difficult. So see here what I can do. Instead of this 2 pi r length, I can go for a subtended angle. So how I can measure this angle in your cycloid? You have already seen. What is this subtended angle will be for a cone?
Theta is equal to 2 pi r.
This theta will be, if this is 2 pi r, theta will be the subtended angle. Angle will be theta will be r by capital R into 360. How it is got? It is a segment length. Suppose this is R. This is R. This is smaller. Okay. This R into this theta will be equal to my 2 pi r. Right. So that I will get this theta will be R by capital R into 360. So already we know. R is nothing but my generator length. So what is the generator length? This is 63. So 20 divided by 63 into 360, how much you are getting? Angle we are getting as 114.2 degree. Right. So 114.2 degree, okay, something like this we will be getting. Right. We cannot measure this and we have to divide that into 12. Okay. It is not possible. What we can do it in an easy manner. See here, as for development for you in exam. So this angle we know it is going to be 114. We just represent that 114. Right. So then that 114 divided, okay, 114 degree, can you measure it in your draft? 114.2. So 115 you measure it. Okay, 115 how you measure? The cone, the development of a cone, just a cone, it will be a radial length. For a radial length equal to the generator length. Okay, generator length what is measured in your front view? That is equal to 63 mm. And to what angle I should draw the segment of this circle for radius 63. So that angle is called subtended angle. That angle will be found by R by R. This R is nothing but my generator length, radial length. Right, that is 63. By dividing that I will be getting 114 degree angle. So the 114, for 114 degree, if I draw a segment of circle, right, that is going to be my development of a cone. Listen, this is the development of a cone alone. Listen all of you. Then you segment this circumference 2 pi r, that into 12 segments. So that you have to divide it into 12 equal segments, that circumference. So how I can divide it? This angle 114 degree, I have to divide it into 12. So angle 114, if I divide it, how much I will get? 10 point, how much? 12 divisions, 9 points you will get, 9.51. So 9.51, for 9.51 degrees, you have to get 12 divisions. Listen all of you, as for your exam point of view, either you measure this angle 9.51, okay, that is a right procedure. Okay, similarly you have to measure this angle 114 degrees, then you have to get the development of the cone. That is the right one. So once you have got this, you have drawn this, okay, for this angle, okay, development, what you can do this, either you can use this or the circumference length. What is that? Circumference length, that is 125.6. That you do it by dividing that, I will be getting 10.4. So 10.4 you cut it in your along this R. For 10.4 you measure it in your compass, cut it along your R. Otherwise this segment of R you measure it in your, but it is not correct. Exactly, it is not right. So the angle you have to divide it into 12 divisions. That is a correct procedure. So for your easiness, quickly to do this development, you know that you have to divide that angle into 12. That is an exact procedure. Now what you are taking, the segment length alone you measure it. The segment length is, either it is dividing the circumference length 125.6 divided by 12, that is 10.4. The 10.4 you cut it along this circumference, okay, on your development. So 12 segments you will get. You get 12 segments, then you show the generators, 12 generators. Make it fast. See here. Circumference points, right? Circumference locations. Listen. The first cutting plane, to form the lamp shape, it cuts parallel to the base and perpendicular to the axis, something like this, and 10 mm away from the apex. Right? Once it cuts, I need not show cutting point. You see, it cuts all the generators, 12 generators it cuts, 12 cutting points I have to mark. So for 12 cutting points, the length will be same from the apex. Right? So what I can do is, this portion alone, you look at this top portion after cutting. The top portion alone, it's again something like a cone. The top portion, whatever the removed portion, after sectioning a parallel cutting plane, so this portion alone, it is something like a smaller cone. So to form this smaller cone, what is the radial length I have to measure it? The extreme length, not 10. 10 is the vertical height, okay. The height of this smaller cone, 10. So that is the generator length will be this one. So you measure it in your compass, the generator length. Similar to OG, the generator length for this is this much. Okay, that you measure it in your compass. So using this center, right, using that center, you draw an arc. Okay, that portion continuously, that's the so you need not show the cutting points here. So since the first cutting plane cuts parallel to its base, the top portion is something like a smaller cone. So for that smaller cone, what is the generator length? That you measure it in from your front view. Using that in your compass, directly you cut an arc similar to a bigger cone. So that is nothing but my first cutting points. You need not mark cutting points and you need not transfer it. Right? Just you try, you show it something like a arc. Right? Something like a smaller cone you generate it. You develop it. Right? Then you represent the second cutting plane, which is passing through one of the extremes and it is 25 degree incline. You represent another cutting plane, so 25 degree incline. Right. Now for this cutting cutting plane. You represent the cutting point. So this is 25-degree incline. For this cutting plane, you represent the cutting point. How many cutting points I will get for this? 12 cutting points. You have to mark it. These 12 cutting points you have to transfer it. This is right. These cutting points you have to transfer it in your development. So how to transfer these cutting points? You should be careful. Listen. Once you have got these cutting points, right? 12 cutting points if you are representing. These cutting points you have to transfer it. So cutting point 1 is on the extreme point. So where I will have my cutting point 1 in my development. So this is the location. I will have my cutting point 1 at A, exactly at A. Similarly at the end I have A. So here I will have my cutting point 1. Right. So cutting point 2. How I can transfer that cutting point 2? In my generator. Cutting point 2 is on which generator? Cutting point 2 and 12. Cutting point 2 and 12 is on BO and LO. So how I have to transfer? So on BO and LO, I have to mark somewhere. Cutting point 2 and 12. So how I have to mark that? Listen. How I have to mark this? Listen carefully. These 2 and 12 cutting points. Directly I cannot measure this length. Listen. This 2 and 12. It is. I cannot measure. This is not an actual generator. Right. It doesn't give me the true generator length. So which one will give me the true generator length? Which generator? OG and OA. So I have to project this 2 and 12. I have to project this 2 and 12 to OG. To OG. Right. So that is the location. I have to measure the length for 2 and 12. I have to project that to OG. So along OG. So what is this length? Along OG, what is this length? Or otherwise from O to this point 2. So I have to measure this 2. So I have to project this 2 to a generator which is showing the true generator length. I have to project this cutting point to a generator which is showing true length. So the generator showing true length is my OG. So I have projected that cutting point to that generator. So along that generator I have to measure that distance. That distance has to be transferred to which generator? Exactly. It is OB and OL. So exactly that distance has to be transferred OB and OL. So this is my 2. This is my 12. Right. Similarly this cutting point 3 and 11. Cutting point 3 falls on K, C. 11 is falls on KO. So you project this to the extreme generator, that is which is showing my true length of the generator. So to that generator you project that. So this will give me 3, cutting point 3 and 11. So this distance, either O to 3 or G to 3 you measure it. That length you measure it, G to 3. So I have to mark it exactly on G to 3. C and, so the 3 and 11 is exactly on C and K. So K I have to measure it. So this is my 3. So this is my 11. Is it clear? Similarly, all the cutting points. Listen again. Okay, this is an important how to transfer the cutting point in a cone or pyramid. Right. So this cutting point has to be transferred, okay, to an extreme generator as for cone. extreme generator only, since the extreme generator only shows the true length of the generator, right? So all the points has to be transferred to the extreme generator, which is a generator showing true length. So then you have to measure the cutting point distance from their apex or from the base, right? So then that distance has to be transferred on a corresponding generator in your development, right? Once you have transferred all the points, try to join the cutting points in as a smooth curve. Since it is a cone, I have to join it as a smooth curve. So this is a thing. Cutting points I have joined as a smooth curve here. Listen, in my development. Then, which is the lampshade portion I have? So in between these two cutting plates. So this is the portion is my lampshade. In my front view, this is the portion is my lampshade. So this is my lampshade. Right. So that portion alone you have to darken it, excluding inner generators. Right. So you see here only the extreme portion you have to darken it. Skipping the top portion of the first cutting plane, bottom portion of the second cutting plane. So inside to that, so only the extreme portion you have to darken it. So this is the development of my lampshade. If I roll this, I will form a lampshade something like this. Right? Is it clear? You have any clarification in this? So as for cone cutting point, you have to transfer it to the generator which is showing the true length. That is the extreme generator. Right?